So this video presentation will be all about steady state exercise. So in the first half of the presentation I'll be talking through with you what steady state exercise is and things that change inside the body physiologically due to steady state exercise, and in the second half I'll be going through and analysing some of the data that I collected from a steady state exercise test that I completed on a few athletes. So what actually is steady state exercise? Steady state exercise is defined as activity that achieves a balance between the energy required by working muscles and the rate of oxygen and delivery for aerobic ATP production. How should steady state exercise look? So it should steady state exercise is long continuous exercise that is completed at the same speed and intensity throughout the whole duration of exercise. So if we take a runner for example, the runner should be running at the same speed and intensity. You shouldn't see any change in speed throughout the whole of the run. Same with also a cyclist or a swimmer. So there are some examples of how steady state exercise can be completed. And running at the same speed and intensity allows for all the body systems to work at a continuous rate and speed. So from running at the same speed or swimming or cycling, it allows for all of the systems, for example the cardiovascular system, to meet the demands of the exercise and then continue working at the same rate. So now I'm just going to talk about heart rate during steady state exercise. So during the initial stages of exercise, our heart rate will always increase whether we are working aerobically or anaerobically. The basic explanation for why this happens is because the conduction of the heart must occur quicker to ensure enough blood gets to the working muscles. However, a lot more happens within the body to inform the heart that it must contract quicker. It all begins at the receptors. Receptors around the body detect multiple changes in the body due to the start of exercise happening. Proprioceptors detect change in movement. Chemoreceptors detect a change in the acidity of blood, so for example more CO2 developing in the blood. Thermoreceptors detect a change in the body's temperature, and finally baroreceptors detect a change in overall blood volume. These receptors then send signals up to the cardiac control center, which is located in the part of the brain called the medulla oblongata. An impulse is then sent out of the cardiac control center down the sympathetic nervous system, where noradrenaline is released into the SA node, consequently making the heart beat faster. So this process happens at the start of steady state exercise, which is clearly shown on the normative data graph. We can see at the beginning there is an increase in the heart rate. However, at around 5 minutes in, during steady state exercise, you should see a plateau in heart rate. In other words, heart rate remains constant throughout the remainder of exercise. The reason for this happening is due to the fact that during steady state exercise you're working at the same intensity, meaning that once the cardiovascular system has met the demands of the exercise, it can then also remain working at a constant rate, which is what causes this plateau throughout exercise. Finally then, at the end of steady state exercise, we should see quite a fast drop in heart rate back to resting heart rate, due to there not being a high oxygen debt to pay back. So now I'm going to talk about cardiac output and stroke volume in steady state exercise. So very simply, stroke volume is the amount of blood that is ejected from the heart per beat. As exercise starts, stroke volume increases due to the demand from the muscles needing more oxygen to fully function. Oxygen is carried to the muscles in our blood, consequently meaning that if stroke volume increases, there will be an increase in oxygen at the muscle site to be diffused into the muscle. During steady state exercise, stroke volume initially increases when going from resting to exercising, but then after that it gradually begins to plateau due to the exercise being completed at a continuous speed, meaning that the heart rate will also be beating at a consistent speed, ejecting the same volume of blood per contraction. A big factor that affects stroke volume is venous return. So venous return is the volume of blood that enters back into the heart via the vena cava. The higher the volume of blood that enters the heart during the diastole phase, so the relaxation phase, which creates an effect of stretching the ventricular walls, the higher the stroke volume will be. In other words, the more blood that fills the heart, the more that can be ejected out during systole phase. On the other hand, cardiac output is the volume of blood ejected from the heart per minute. Cardiac output is determined by heart rate and stroke volume. If either heart rate or stroke volume increase, or both, cardiac output also increases. Cardiac output increases proportionally with exercise intensity. So due to stroke volume and heart rate both increasing at the start of steady state exercise, so does cardiac output, and this also applies to when stroke volume and heart rate plateaus. When both stroke volume and heart rate plateaus, so does cardiac output. So finally, I'm just going to talk about the difference between stroke volumes in a professional athlete like Mo Farah and your average person. So if we look at the data I have on the screen about Mo Farah's cardiovascular system compared to your average person, you can see a major difference. So the average resting stroke volume for a human being is about 70 to 80 milliliters. So every beat, 70 to 80 milliliters of blood is ejected from the heart. Whereas Mo Farah's stroke volume at rest is 110 milliliters. And I also have here during exercise, his stroke volume can rise to 200 milliliters. And also I have Mo Farah's resting heart rate being 33 beats per minute. Now I will come on to explain to why this is the case. So Mo Farah is one of the best long distance runners in the world, who has spent years and years completing cardiovascular training to improve his cardiovascular endurance. When performing cardio, blood flow is directed towards the working muscles and away from areas that aren't doing much, such as your arms during running or the digestive tract. There is an increase of blood flow and blood volume returning to the heart. As the heart registers a larger blood volume, over time, the left ventricle adapts and enlarges. This larger cavity can hold a higher volume of blood and can eject a larger volume of blood even when at rest. Also, over time with chronic cardio training, our resting heart rate drops because each beat delivers a bigger burst of blood due to the increased cavity, and therefore fewer beats are needed. This explanation is clearly backed up by Mo Farah having a resting heart rate of 33 beats per minute and having a stroke volume of 110 milliliters, which is around 40 to 30 milliliters above the average person. Therefore, when it comes to completing steady state exercise, Mo's stroke volume becomes really efficient, and he will be sending large amounts of oxygenated blood down to his working muscles by not even needing to get his heart rate that high. Whereas your average person's stroke volume would be a lot lower during steady state exercise, which means their heart rates will need to work a lot harder to get the sufficient amount of blood to the working muscles. So now I'm going to talk about breathing rate during steady state exercise. So when we start exercising, one of the immediate effects is the breathing rate increasing. So the reason for this is because of receptors detecting changes in the body, same as heart rate. Receptors detect a change in movement, temperature change, blood volume, and also an increase in CO2 in the blood. These receptors then send signals to the respiratory control center, which is found inside the medulla oblongata in the brain. After that, it moves into the DRG, and the DRG is then what sends an electrical impulse down the intercostal nerve and finally into the intercostal muscles. These signals inform the intercostal muscles to contract more frequently, therefore increasing the depth of breathing, which means a higher volume of oxygen can diffuse across the alveoli into the bloodstream, which it will then bond with hemoglobin. Due to there being an increase in heart rate, your blood pumps through your muscles at a faster rate, leaving less time for oxygen uptake. Having more oxygen available in the blood from a faster breathing rate helps the muscles get the amount they need. Additionally, an increase in depth of breathing also ensures that CO2 that builds up diffuses across the alveoli to then be breathed out from the lungs. During steady state exercise, as well as the cardiovascular system, breathing rate plateaus because of the respiratory system meeting the demands of the exercise. During steady state exercise, you should be working consistently at moderate intensity, which allows for the respiratory system to work at the same rate. Breathing rate and depth of breathing should remain the same. This will obviously change if intensity increases. So now I'm going to talk about Starling's law. So Starling's law, as described by Adams et al., states that stroke volume increases in response to an increase in blood volume filling the heart. So in simpler terms, the more blood that fills the heart during the diastole phase, which is the relaxing stage of the heart, the greater the amount of blood that will be squeezed out of the heart when it contracts, or otherwise known as the systole phase. A few key terms in relation to Starling's law are end diastolic volume, preload, and stroke volume. I've already described stroke volume as being the amount of blood being ejected from the heart per beat, but preload is when there is a maximum amount of pressure being put on the walls of the ventricles, causing them to stretch as far as they can possibly go. And end diastolic is the volume of blood laying in the ventricles before the contraction of the heart takes place. So having a greater end diastolic volume is what Starling's law says would increase the contractile strength of the ventricles and will consequently increase stroke volume. The reason why this happens is because the myocardium, which is the muscle tissue of the heart, becomes more stretched, therefore increasing sarcomere length, resulting in an increase of sensitivity to calcium ions, which consequently causes a more stronger contraction of the heart. At the onset of exercise, your blood pressure rises for a few reasons. Firstly, heart rate and stroke volume increases because hormones such as noradrenaline get released into the SA node. These cause the heart rate to beat faster and harder. This consequently pumps more blood out of the heart and into your vascular system. There is a high volume of blood applying pressure on the artery walls. Secondly, as your muscles contract, they squeeze against the veins, and this causes momentary but significant increase in blood pressure. Typically, it is mainly your systolic pressure, which is the pressure in the arteries as your heart is pumping blood out, that rises, and not much so diastolic pressure during the relaxation of the heart as it fills for the next contraction or beat. To conclude, your blood pressure does rise initially when exercise begins due to changes in the cardiovascular system. However, when the cardiovascular system meets the demands of steady state exercise and heart rate plateaus, so does blood pressure. So now we're going to talk about neuromuscular response. So to allow for coordinated movement patterns of the muscles, Golgi tendons and muscle spindles provide sensory information about the intensity of exercise. Muscle spindles are sensory motor organs located within the skeletal muscle. So each muscle spindle is made up of 3 to 5 specialized muscle cells known as intrafusal cells. These cells, which are bundled together by a layer of connective tissue, lay alongside the rest of the skeletal muscle fibers. So when intrafusal cells detect a change in your muscle length, they send an impulse to the central nervous system about the degree of stretch in the muscle. The central nervous system relays information down to the neuron inside a motor unit, causing all the muscle fibers in that unit to contract. The amount of force you generate at any given time depends on how many motor units your body is calling for. So for example, if you're picking up a pencil, your motor units will generate only as much force as you need to pick up that pencil. When it comes to steady state exercise, the body gets used to it the more efficient the muscle spindles become at transmitting information to the central nervous system, and therefore consequently allowing for smooth muscle movement to be implemented. On the other hand, the Golgi tendon organ is located where the muscle fiber or skeletal muscle meat tendons. It is made up of strands of collagen, and it also contains